So before we start trying to do more advanced factoring techniques with rational zeros theorem, I wanted to quickly discuss a good practice to always follow when you're factoring any sort of function. In general, y'all, if you're factoring a function, you should always look at all the terms first and determine if any of them if they all have a common factor, if there's anything in common between all of them. So in this function f of x that I have here, I can see that every single one of my terms has a factor of 2, right? Every single number is even, and they all have a factor of x. So what I'm going to do is I'm going to start off by factoring 2x out of this. So if I pull 2x out, what does that leave me with? It leaves me with 2x squared minus 3x minus 5. So right away, I have already factored this a little bit and made the rest of my work a lot easier on me. It's going to be a lot easier to factor this quadratic than it was going to be to factor this cubic function, right? Because right now, this one is actually quite easy to factor. 2x stays, right? I'm going to do the double cheek method. Y'all could do diamond if you wanted. I would have 2x squared would be 2x and x. And 5 would be 5 and 1. To make this happen, I'm going to do 2x minus 5 and x plus 1. Because minus 5 times 1 is minus 5. Minus 5x plus 2x would make minus 3x. And here it is in factored form. So just always be on the lookout, y'all, of can I pull any common terms out or any common factors out of all of my terms. So now we find ourselves faced with what is known as the rational zeros theorem. Now, the formal definition of it looks quite complicated. However, once you start getting the hang of what it is really about, seeing some examples, it should hopefully make a bit more sense. So first, we're going to start off with the formal definition of it. So rational zeros theorem is in principle about figuring out what are the potential zeros, the potential x-intercepts for a polynomial, okay? So if I have some polynomial, f of x, and this is our general polynomial, right? A sub n times x to the power of n plus dot, 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 all the way to a sub naught, right? The two things that we care about in this are the leading coefficient and the constant at the end of the polynomial. These are the two pieces of the polynomial that we're going to worry about with rational zeros theorem, okay? So a sub naught, what I'm going to do is I'm going to let my variable p represent some factor of a sub naught. In fact, it could represent, it is all of the factors of a sub n, I mean. And q is going to represent all the factors of a naught. Now, what do I mean by factors? This would be a good time to probably introduce an example polynomial. So here I have the function f of x equals x cubed plus 5x squared minus 25x minus 125. This is a higher degree polynomial, meaning that the degree of it is greater than 2, right? So the degree is greater than 2. And this is going to be the case when you want to use rational zeros theorem. If your degree of the polynomial is 2 or less, then we don't need to use rational zeros theorem. We could just factor it using our quadratic factoring techniques. Okay, so we have f of x equals x cubed da 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 minus 125. So in this problem, my p value is 1, right? P is going to be, p, if you guys remember, I said is all the factors of the leading coefficient, okay? So the only factor of 1 is 1. All right, well, let's look at q. What are all the factors of the constant 125? Well, 125 could be, the factors of 125 are 1 and 125, right? Because 1 times 125 makes that. As well as 5 and 25, because 5 times 25 makes 125. Remember, guys, that's what I'm talking about when I say the factors of the number. Another interesting thing, though, because positive and a negative number can multiply to a negative, or negatives and positives. Because of the way that positives and negatives can multiply with each other to create both positive and negative numbers, all of these factors I need to consider as being plus or minus. Okay. So I have that P is plus or minus 1 and Q is plus or minus 1, plus or minus 5, plus or minus 25, plus or minus 125. It's just the factors of the constant and the factors of the leading coefficient. Okay. So how does rational zeros theorem actually work? The idea of rational zeros theorem is that if I take my Q values, the factors of that constant, and I put them all over my P factors, the factors of the leading coefficient. So I have Q divided by P. And I just generate a list of all the possible combinations. Then it will give me a list of all of the possible factors or the possible zeros of the original polynomial. So what that looks like is I take all the Q values. So I have plus or minus 1, plus or minus 5, plus or minus 25, and plus or minus 125, all over plus or minus 1. And I say, okay, so what are all of the possible combination outcomes of these, right? Well, 1 divide 1 would be 1, but I'm going to keep the plus or minus. 5 divided by 1 would be 5. 25 divided by 1 would be 25. You kind of get the idea. And 125 divided by 1 would be 125. So what this has just created is a list of, this is actually 8, because I have plus or minus on all of them. This is 8 different possible zeros for my polynomial. What that means is like, if this polynomial is to be factored, all of the all the zeros, the x-intercepts for this polynomial would be contained within this list. Okay, so really what rational zeros theorem is all about is just generating this list of possibilities. Because once I know my possibilities, I can then test them and actually solve for the factors. Now I want to do, before we continue on, I want to do one more example of that P and Q with the rational zeros theorem for a different type of problem. So here I have g of x equals 2x to the 4 plus 3x cubed plus 8x squared plus 12x. Remember, we said before that it would be good practice to look at all the terms and factor anything out that they have in common. What do all these terms have in common? They all have an x. So I'm going to factor x out of this polynomial first. So I would have x times 2x cubed plus 3x squared plus 8x plus 12. Now I'm going to focus on these guys for my P and Q. So my P is, remember, the factors of the leading coefficient, so 2. So it'd be plus or minus 1 and plus or minus 2. My Q will be the factors of the constant. So that is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minance 12. Those are all the possible factors of 12, right? 12 is crazy because 12 has a lot of factors, but we'll be able to deal with it. It's fine. So now, by rational zeros theorem, what I'm going to do is I'm going to take my Q factors and divide them by the P factors and generate a list of possible zeros. Okay, so P over Q would be plus or minus 1, plus or minus 2. I'm just going to copy this list here. Plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12, all over 1 and 2. Now then this one's going to, what I'm going to do is I'm going to say, okay, so then what are all of the possible x-intercepts, all the possible zeros? This is what rational zeros theorem does. It generates a list. So I just need to look at all the possible combinations. So 1 over 1 would be 1. 2 over 1 would be 2. 3 over 1 would be 3, right? Keep going with that. 4 over 1 would be 4. 6 over 1 would be 6. And 12 over 1 would be 12. Okay. But it doesn't just stop here, because look, I also have the possibility of p being plus or minus 2. So 1 over 2 is 1/2. So plus or minus 1/2. 2 over 2 is 1, which I've already covered, so I don't need to add it. 3 over 2 is 3/2. 4 over 2 is 2, which I already have. 6 over 2 is 3, which I already have. 12 over 2 is 6, which I already have. So that means that my list of possible zeros, my list of possible x-intercepts for this function are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12, plus or minus 1/2, and plus or minus 3/2. So the next thing for us to do when we're factoring these higher degree polynomials after we've created the list of possible zeros is to just test those zeros. So what we're going to do is we're going to end up looking at another technique which will help us determine which of these is the actual zeros, which are the actual factors of this polynomial. So now that I've generated this list of possible zeros, remember guys, what rational zeros theorem was doing is helping me create a list of potential zeros. I'm not claiming that all of these are the intercepts of this function. They are just possible intercepts. Now that I have this list of possible zeros, I need to test them and figure out which ones are the real ones. The way that we're going to do that is using something called the polynomial factor theorem. Polynomial factor theorem tells us that if I have some polynomial p of x, so if p of x is a polynomial, I have some value that I plug into it, like a, and p of a. So when I plug a in, it equals 0. Then x minus a is a factor of p of x. So what is this actually saying? It's actually quite logical to think about. It's claiming that if p of x is a polynomial and I plug some number into that polynomial, which makes it equal 0, then x minus that number must have been a factor. That should make sense, right? Because if x minus a was a factor, like let's say p of x was equal to like x minus a times x plus b or whatever, right? Let's say this is the factored form of this polynomial. When I set that equal to 0, I would find that the factors x minus a equals 0 itself. So x should equal a to be a solution, right? So really what we're doing is we're taking advantage of the fact that when you plug the zeros of a polynomial into that polynomial itself, it makes the polynomial equal to 0. That's kind of like definitionally true. So what that looks like in an application, I'm going to take these possible zeros, plug them into my function, and see, does this actually equal 0, right? When you're doing this, that's going to be a lot of calculation, right? There are some techniques and strategies to make this easier on yourself. For example, I'd suggest starting with your plus or minus 1 when you're doing this, just because it's pretty easy to plug 1 in, right? When I plug 1 into this, when I have f of 1, what do I get? I get 1 cubed, that's 1, plus 5 times 1 squared, that's 5, minus 25 times 1, minus 125. So you see I've plugged 1 into the function. Does this equal 0? Does this equal 0? That's the question, right? That's always the question. Does it equal 0? Clearly, this is not going to equal 0, right? Minus 125 is not going to be countered by these things. So if it doesn't equal 0, then this is not one of my zeros for the function. Okay, let's test the negative then. Let's test -1. F of -1. -1 cubed would be -1. -1 squared is 1 times 5 is 5. -1 times 25 is plus 25. And -1 minus 125 stays. Does this equal 0? Question mark? No, that's not going to equal 0. So I know that f of -1 is not a solution. Okay, let's try 5, right? And I just keep going like this, right, guys? So I say, okay, well, what is f of 5? I plug 5 in. 5 to the power of 3. 5 to the power of 3 is actually going to be equal to 125. 5 squared is 25. 25 times 5 is another 125. Minus 25 times 5, 25 times 5, we just said, was 125. And minus 125. Does this equal 0? It does, right? 125 minus 125. 125 minus 125. It will actually equal 0. So I know, therefore, that this is a solution. Okay? So what this means for me is that one of my x-intercepts in this polynomial is at 5. And the factor that corresponds with that would be, right? The factor would be x minus 5. So what's happened here, y'all, is that my polynomial factor theorem has allowed me to determine that one of these zeros was an actual 0 of it, and it was 5. As soon as you guys find a single one of the zeros, I would suggest you stop. As you can see, the process of polynomial factor theorem is a bit tedious, right? So what we're going to do is, once we have found one of the factors, x minus 5 here, we're going to factor x minus 5 out of this polynomial and then see if we're looking at a better situation after that. Okay? So that's going to require us to do just a few more steps of math. Before we start talking about how to factor out the higher degree polynomials, let's look at our other example, g of x, that we had done before. We had found that these were all of the possible zeros for g of x, and we should probably go ahead and test them. So what I'm going to do is I'm going to first test x equals 1 and -1. And you'll notice that because I had already factored x out, I don't need to worry about that. I'm only going to worry about plugging it into this piece here. So when I plug 1 into this, I get I get 1 cubed. So here, let's see. When I have g of 1, I get 1 cubed is 1 times 2 is 2. 1 squared is 1 times 3 is 3. 1 times 8 is 8, and plus 12. Now this is all things adding, so there's no way that's going to equal 0, right? It's all a bunch of things adding. This is actually something that I wanted to point out. If you ever have some sort of polynomial and you're trying to figure out through rational zeros theorem what the zeros are, if every single term is adding, the only way that this can actually equal 0 is if some of these end up subtracting, right? How could I have made some of these subtract? That would be through negative x-intercepts. So actually, because every single one of these terms is adding, I can already recognize that none of these should be positive. That's just a little trick that sometimes can make our life easier. Kind of thinking about things like that. So let's try some other zeros. What about -1? When I plug -1 in, what do I get? So g of -1 is equal to -1 cubed is -1 times 2 is -2. -1 squared is +1 times 3 is +3. -1 times 8 is minus 8, and then plus 12. Will that equal 0? No, it's not going to, because this would be 1 minus 8 is negative 7 plus 12 is 5. So it does not equal 0. All right, let's try negative 2 then. G of negative 2 equals negative 2 cubed is going to be 8. Negative 8 times 2 is negative 16. Negative 2 squared is 4 times 3 is plus 12. Negative 2 times 8 is minus 16. And then plus 12. You can see that I've gotten something. Negative 16 and 12 makes negative 4. Negative 16 and 12 makes negative 4 for a total of negative 8. That is not 0. But there is something important here, y'all. There's something important here to notice. It may not equal 0 here. Hey, wait, let me put that back. It may not equal 0. But what did I get for these solutions? When I plugged a negative 1 in, I had gotten before 5, I believe. Yeah, it was equal to 5. When I plugged negative 2 in, I got negative 8. Do y'all see something? At negative 1, it was positive. At negative 2, it was negative. So where is 0? 0 is between this. 0 is between a positive and a negative number, right? Well, what's between negative 1 and negative 2? Negative 3/2. You see that? I have a feeling that if I plug negative 3/2 into this function, it will equal 0, because negative 3/2 is between negative 1 and negative 2. And 5 and negative 8 has 0 between it. This is an extension of an idea that we will talk a lot more about in the future, but for now, we will just try it out. Try out our hunches. So what is G of negative 3/2? Amabril, this is one that you might want to end up pulling out the calculator for this guy. But you'll see that if you do end up plugging it all in, it equals 0. So one of my solutions here would be x equals 3, negative 3/2. What does that look like as a factor? Some people might be asking me. Well, to get it as a factor, you would just, all you have to do is get it so that this is an equation equal to 0. So I would add 3/2 over. So x plus 3/2 is the factor. If you don't like fractions, what you can do is you can multiply both sides by 2 to get rid of that fraction. Right? 2 times 0 is still 0. 2 times x is 2x plus 3. So really the factor is 2x plus 3. So to recap what just happened, I was plugging in values to see which one would make the function equal to 0, right? I did use a little trick where I recognized that if x equals negative 1 was too big, and if x was equal to negative 2 was too small, then something in between must have been just right. Yeah, it's kind of like Goldilocks out here. And the last thing was if your 0 is a fraction, you can leave the factor in with a fraction, or you can get rid of the fraction by calling it, by multiplying by the denominator, right? So now let's go ahead and finally look at how do I then factor this out? How do I factor 2x plus 3 out of this polynomial? So the last thing that I need to do in order to factor this higher degree polynomial, x cubed plus 5x squared minus 25x minus 125, the last thing I need to do is to just actually factor it. Something that you may or may not have noticed by now is that factoring is very similar to division. So what I'm going to do is I want to take my polynomial and divide by x minus 5, because that is the factor I'm trying to pull out. How do we actually do this? How do we divide polynomials? We actually do it through a technique you may have learned in Algebra 2 called polynomial long division. So I take my polynomial x cubed plus 5x squared minus 25x minus 125, and I want to divide it by x minus 5. you're going to see that this looks actually very similar to normal long division. All right. So what we're going to do is this. We look at our leading term and our other leading term, and we say, what do I need to multiply x by to equal x cubed? I need to multiply it by x squared. Okay. I'm going to actually use a different color to differentiate things. I need to multiply by x squared. Okay. X squared times x is x cubed. X squared times minus 5 is minus 5x squared. Okay. So what I'm doing is I'm recognizing that in my solution, having this x squared is going to be the equivalent, when it's multiplying with x minus 5, of x cubed and negative 5x squared. So I have x cubed and I have negative 5x squared covered, right? So then what I do is, just like in normal long division, I would subtract that. So x cubed minus x cubed cancels out. Excellent. 5x squared minus negative 5x squared. If I subtract a negative, that makes it plus, right? So 5x squared plus 5x squared is 10x squared, huh? And then I'm going to bring down this guy, minus 25x. Okay. Let's look at the next one then. What do I need to multiply x by to get 10x squared? I need to multiply x by 10x to equal 10x squared. So I get plus 10x. And then I multiply it back and subtract just like I did previously. So I say, okay, 10x times x is 10x squared. 10x times minus 5 is minus 50x. And I need to subtract this, right? So 10x squared minus 10x squared cancels out. Negative 25 minus negative 50. That's going to be plus 50, right? So negative 25 plus 50 is positive 25x. All right, cool. So now I can bring that down, and I have 25x minus 125. And I say, okay, what do I need to multiply x by to get 25x? 25, right? So plus 25. 25 times x is 25x. 25 times minus 5 is minus 125. And what do you know? When I subtract by this, you'll see 25x minus 25x cancels out. Negative 125 minus negative 125, that's plus. These cancel out. And I'm left with 0, which is perfect because 0 is my remainder, which means that these are a perfect division. Therefore, my polynomial, the original one, f of x is equal to x minus 5, which I just divided out, times the result, x squared plus 10x plus 25. Now, I'm not quite finished factoring, am I? I still need to factor that quadratic right there. But here's the wonderful thing about it. This is why I didn't bother when I was doing up here rational zeros theorem. This is why I did not bother finding every single zero for this polynomial. I just wanted to find one. Why did I only want to find one? Because then, once I've found one, I divide it out, and I'm left with a quadratic, which we know how to factor by the diamond method. We could do it through the double cheek method. Anything is really better than rational zeros theorem. The reason why we use rational zeros theorem to do all this is because we have to when we have a degree greater than 2. Okay, so as soon as you can get it to this form, we then just can factor it using our standard means. Maybe the diamond, 25 on top, 10 on bottom. What multiplies to 25 adds to 10? 5 and 5. So in the end, f of x is equal to x minus 5 times x plus 5 times x plus 5. which is equivalent to x minus 5 times x plus 5 squared. Look at that. So it's completely factored. My cubic function is factored. And I know all the x-intercepts. X-intercepts are going to be 5 and negative 5. This one here, because it's being squared, would be a multiplicity 2. I know the y-intercept because of what we've done previously. The y-intercept would be negative 125, right? The constant. And I could actually now, at this point in time, go ahead and plot my intercepts, understand the end behavior, and I could actually sketch the graph of this function. So before we conclude this video, I just wanted to do one last of the polynomial long divisions with our second example for g of x. So previously we said that g of x was x times 2x cubed plus 3x squared plus 8x plus 12. And we had figured out that 2x plus 3 was one of its factors. So I'm going to do polynomial long division to factor this out here. So I have 2x cubed plus 3x squared plus 8x plus 12. And I am dividing it by 2x plus 3. So what I need to multiply 2x by to get 2x cubed? I need to multiply by x squared. So x squared times 2x is 2x cubed. X squared times 3x, or times 3, I mean, is 3x squared. And I subtract that, right? Oh, what do you know? 2x cubed cancels out. 3x squared cancels out. So I'm actually left with nothing here. So then what we're going to do is we're going to bring down 8x and the plus 12. So now I need to think, okay, what do I need to multiply 2x by to get 8x? 4. You guys notice that I skipped an x term. That's fine. I didn't need an x term, so I don't need to necessarily include it. So 4 times 2x is 8x. 4 times 3 is 12. Subtract that, and what do you know? 8x and 12 cancel out, and I'm left with a remainder of 0. So then we say, okay, so then what is my factored form for g of x? Let's bring that over here. So g of x would be therefore equal to, remember, there was this x over here. Don't forget about it. So we had x times 2x plus 3 times x squared plus 4. So that is the factored form. You'll actually come to see that x squared plus 4 cannot factor any further. If it was x squared minus 4, then we could do difference of squares. But because it is adding, you cannot. So what are my zeros? What are my intercepts for this? Well, if I set g of x equal to 0, then each of these individual factors would be equal to 0, right? So I'd have x equals 0, 2x plus 3 equals 0, and x squared plus 4 equals 0. That 4 don't look so good, huh? Let's fix it. So solving these, we get the solutions to g of x are 0. This one I would subtract 3 from both sides and divide by 2 to get negative 3 halves. And over here, I would subtract 4 from both sides. X squared equals negative 4. Square root it. And hey guys, what happens when I square root a negative? Do y'all remember what we get? What is the square root of, what's the square root of a negative? Remember guys, that gives us those imaginaries. So, it gives us that complex number, right? So what we get is we say, oh, okay, then this is equal to, well, the square root of 4 is 2, so 2i. And it would be positive or negative because, remember, when you square root while solving, you should have a plus or minus actually. So my solutions are 0, negative 3 halves, and plus or minus 2i, where I is that imaginary number square root of negative 1. So interestingly enough, y'all, if you get if you get a complex 0, right, like this, if this is a 0, what happens is that this won't actually, there's no 2i on the x-axis. Like when I'm sketching this graph, there is no 2i. So it would cross the x-axis at 0. It would cross the x-axis at -3/2, and those would be the only points of intersection for the x-axis. So the moral of the story, y'all, we use the, I'm going to zoom out a bit on my work here. We use the rational zeros theorem to find a list of possible zeros, right? Based on the lead coefficient and the constant. Then we use polynomial factor theorem, right, to test those zeros. We said, okay, if I plug it in, does it equal 0? Once you find one that does equal 0, that gives you the factor, right? Because if the 0 is at 5, then the factor is x minus 5. And finally, you use long division to divide that factor out. This is a bit of a long process. I'm aware of that. So that makes it annoying and it makes it intimidating to use. But I promise you guys, the process is actually very consistent. It really doesn't deviate a ton. And so if you just use this and you practice it a couple times, you'll get the hang of it. And it becomes like clockwork. All right? Y'all got this. Good luck on your homework. Have a good day.